All right, so we'll go ahead and start. So again, as I mentioned before, my name is Sheyi Shambore, and I will be taking you through today's webinar of flow simulation using FloEFD. Just a couple things to get off by the way of housekeeping. First off, this webinar will be recorded, and afterwards the recording will be posted on our company YouTube channel, and from there I believe the links are also then uploaded to our website as well. So everyone that attends this webinar will be able to get access to this content afterwards. Next off, all the attendees are muted in today's GoToWebinar, and so if you have a question or a comment that you'd like to pass on to the organizers, on the right-hand panel of your GoToWebinar control pane, you may have to click on a little red arrow to expand it out. But in that right panel, it's a gray panel, and there's a box in there for questions. You can type in any questions you have in there, and that will pass on to the organizers here. We'll review the questions and then answer them, on air. Right? And then the other thing to point out as well, if you look at the name of the organizer in your GoToWebinar control panel, my name is there, Sheyi, and if you right-click on my name, you can copy my email address, and you can, send me an email directly afterwards if you have any additional questions about it. So at this point, I'll go ahead and dive in. And so first off, we're going to just start off with a quick PowerPoint introduction to who we are as Boundary Systems. And so we are a product development and consulting company based out of Cleveland, Ohio, but really we have a reach that expands way beyond that. And we like to say that we help our customers achieve greater levels of success by offering different solutions to any of their product development needs. So whether that be in CAD design or product data management, or even in simulation, as is currently with FloEFD, yeah, we like to say we partner with different companies to provide the best solutions to any of our customers in whatever challenges they may be facing. So the other company I'll introduce as well, before I guess introduce, I'll also just quickly mention we have been growing a lot, as this slide basically shows, and yeah, I'll just leave it at that. The other company I'd like to introduce is Mentor Graphics, and they're the ones that created, or I guess that own FloEFD. And so they are primarily an EDA company, so electronics design and automation is probably the main bread and butter, and they're a pretty big elephant in that market. And they also have a mechanical analysis division that specializes in a bunch of things, one of which is CFD, and that's where FloEFD comes into play. And so FloEFD is a software that comes straight out of Mentor. And so now, so we'll go ahead and dive straight into the software. So FloEFD. Now the way I'll present this is going to be through a couple of, I guess you'd say, unique selling propositions, or not USPs, because we're not selling here. Rather, some key benefits as to that make FloEFD very, very great to use for flow simulation, right? And so I'll start off with the fact that it's CAD embedded. So in other words, whenever you are working with FloEFD, you never have to import or export any geometry file. You never have to worry about saving out a step file conversion issues, or missing surfaces or things like that. FloEFD works natively inside of your CAD tool. So, and it's embedded into CATIA, Creo, SolidWorks, NX, and also Solid Edge as well. And so for all of those, it's embedded natively. Now, if you want the standalone version, yes, there is a standalone version of FloEFD, just like other CFD packages. But the primary reason why they went the standalone, the embedded route, is that it allows you basically now to, you don't have to lose geometry fidelity by translating between one format or the other, right? And then it it reduces the amount of setup time you have to do, right? Because if this was ANSYS Fluent, for example, you would have to first import the model into SpaceClaim and then use SpaceClaim to clean up the model before you can then start to generate your mesh and all of that. In this case, you're using your CAD tool to generate your CFD model, right? And you're already used to, for example, in my case, Creo, right? I could generate a CFD ready model in 90% faster in Creo than I can do in SpaceClaim, which I have no clue what it does, right? So we're not introducing a completely new UI to where you don't know how to use it. We're saying you're used to CAD in your tool. We'll bring CFD to you inside of that tool as well, right? And so that makes your setup 10 times easier. All right. The next thing to also mention is the automated meshing technology. FloEFD has a proprietary and unique Cartesian mesh technology that allows it to basically handle quote unquote dirty geometries much easier and much quicker, and with without as much of a refinement on how you set up your CFD model beforehand. And so really the benefit here then is, you're not spending a lot of manual time meshing the model, right? Um, you don't need to have a huge amount of expertise in creating CFD meshes and the algorithms behind the scenes before you can create an adequate mesh inside of FloEFD. And also, because the meshing technology is fast, it reduces, it generates a mesh in, a much quicker time and then allows you to go ahead and start solving. And yet the mesh is very accurate for solving whatever physics you have, right? And to give sort of an easy example, one of the customers that FloEFD was presented to, they currently at the time had Fluent. And in order to generate a mesh for an LED headlight that they had, it was taking them about 2 weeks to generate a mesh for, to analyze their LED headlight for a car. And really all we did was, bring that same model inside of FloEFD, and in 10 minutes we had a mesh that we could run with, right? And so again, we say that to say it's very, very fast and robust in how it, generates the mesh. All right. So another enabling technology in FloEFD is the user interface, right? And so what we've tried to do is to put as many familiar interfaces as possible inside of FloEFD. So first off, you have things like where it integrates seamlessly with Office-based applications like Excel or Word. So if you want to view graphs or charts or quantitative data from FloEFD, with a one click you can export or push that data to Excel or Word, right? So then that means you don't have to start copying and pasting all this bunch of information. And not only that, FloEFD already has an automated report generation tool already, right? So again, this eliminates the need for spending a ton of time after your simulation creating your documentation, right? And also, there's also wizard-based guides that basically walk you through step by step everything you need to do for your CFD setup. And so again, that makes it much easier to set up as well, right? Another enabling technology inside of FloEFD is the Turbulence Model. And so in many other simulation or CFD tools, you'll have many different CFD, not CFD, you'd have many different turbulence models, right? So sometimes you'd have as many as 5 or 10, or even some even have as many as 20 different turbulence models, right? In this case here, FloEFD has been tuned to use only one turbulence model, right? And that one turbulence model handles all flow regimes. So laminar flow, transitional flow, turbulent flow, even all the way up to, if a space shuttle was re-entering the atmosphere and it's going at, Mach 25 or 30, FloEFD can solve that with the same turbulence model as well, right? And it does not reduce your accuracy compared to other CFD codes. And so what that then means is it's incredibly easy to use, right? For a design engineer who doesn't have a PhD in CFD, there's nothing easier to use than to say, hey, it has one turbulence model that is accurate enough for you to verify whatever physics you have with real world testing, right? Another benefit for FloEFD, I'll actually skip this one for now. We'll come back to that in a second. Another benefit in FloEFD is the way the solver is built. It's very robust, and it always approaches a convergence in 90-something% of the cases. And so it's very, very rare for a FloEFD solve to diverge, at which, in many other CFD codes, that's a possibility that could happen, right? And so you rarely have a case where, your solution diverges and then you have to go tweak some, numerics or solver parameters and then, or some boundary conditions and then rerun it again, only to have it diverge, and then you have to tweak something and then rerun it again. None of that in FloEFD. You set it up once, the solver is robust enough to keep on solving until it converges, right? All right, another wonderful technology inside of FloEFD is the design variant analysis, right? And part of this is because of the what's it called? The CAD embedded functionality as well, right? So because it's embedded into your CAD software and your CAD software is parametrically based, now if you want to analyze a different model, you want to change a dimension, right? Move a component to a different location, right? Make a particular orifice bigger or smaller. All you have to do is change the dimension inside of your CAD model, and you can immediately rerun your analysis or clone your analysis and run your CFD on that, right? So you don't have to export another step file and set up the entire model again with your boundary conditions and your solver parameters and then rerun it all over again. It's as simple as just changing one number, having your CAD model regenerate, and then you can rerun the analysis again, right? And then not only can you also do that in FloEFD, but you can also have FloEFD make those changes automatically as well, right? So for example, I use Creo parametric, and I could tell FloEFD, hey, take this dimension A in Creo and set it to 1, 2, 3, 4, and 5. And for each of those design variables, run a CFD simulation for me using this existing setup. Now I can leave my computer, I can go to lunch, I could go to another project, I could go to the lab and work on something. I can leave my computer running all weekend, and guess what? Whenever FloEFD is done with the first setup, it resets it sets dimension A to 2 and then keeps on running. When it's done with that, it sets it to 3 and then keeps on running, right? And so it saves you, the resource of having to pay someone just to sit at the computer to babysit the model or the software. The software is intelligent. It can run itself and just keep on handling whatever what-if analysis you throw at it. So the last couple of things I'll mention are the smart cells and also the solution adaptive meshing. So FloEFD, in general, with any CFD code, you have solid cells, right, that are inside of a solid body, like in this case, a submarine. You have fluid cells, right, that are entirely inside of a fluid, right, so like in water. And then you have your the cells that are within your boundary layer where you have a lot of a huge flow gradient, right? And with many CFD codes, usually you'd have an extrusion layer within that boundary layer with 4, 5, or 6 different cells in there. And in general, the higher the number of cells you have in there, the more accurate you catch the boundary layer definition, but then also the higher your mesh count becomes, and it just becomes a whole jumbled mess basically. With FloEFD, one of the key enabling technologies is they simplified all of that into something they call a smart cell, right? Which captures and it uses a modified wall function to capture whatever physics is going on in the boundary layer without the need for a high cell count. So typically within one smart cell, you can capture the physics inside of a boundary layer, regardless of if the boundary layer is thin or thick. FloEFD smart cells can easily help capture that physics very, very accurately. And there are many examples where FloEFD is compared to real-world tests and also other CFD codes as well. And it's always very accurate in how it predicts the flow, even in boundary layer driven flows. All right, and then finally, I'll talk about the solution adaptive meshing. And so what FloEFD has is the ability to refine the mesh while it's running in areas of high gradient or flow, right? So for example, you'll notice in these series of screenshots on the over here, with my initial mesh over here, right? I just have sort of a uniform distribution of mesh around everything. But as I begin to move to the right, you'll notice I start to increase my mesh density, or the software, I should say, starts to increase my mesh density on the right towards the areas where I have a high flow gradient, right? And the areas with minimal flow gradient, it keeps those the same. And all of this is done during the run. So again, it makes it much easier to use. You don't have to be a CFD expert in order to use this. It increases your accuracy, right, by refining the areas where you have a higher flow gradient. And it also what's it called? Yeah, reduces your solve time overall, right? Because I don't have to set up 3, 4, or 5 different meshes and run them until I don't notice any change at all, right? FloEFD is just automatically going to keep refining the same mesh and get to a good solution, right? So at this point, I'll pause here with the PowerPoint, and I will switch over to showing a live demonstration of the software. Now, I noticed a couple of you already started, popping in questions into the questions pane. That's wonderful. We like that. If you have any more questions as I've been going so far, please put those into the questions pane. I will get to those, at the end of the demonstration section here. Cool. All right. So I'll switch windows here to Creo Parametric, and then we'll go ahead and show this here. All right, so I currently have Creo open right now, and what I have is just a simple valve model. And really, if I sort of, let's see, I'll hide this part so I can show you what's going on. Well, no, I think I hid the entire assembly. Oh, let's do this here, unhide. Okay, yeah, so it just comes in as one part. But basically, you'll notice, I'll do a Y cross section. Yeah, so you'll notice right over here, basically what this is essentially a ball valve where the ball is set to, I believe in this case, about 40-degree angle. And which means it's going to influence how the flow goes through this piece here. And the challenge is to understand what the pressure loss is just across this ball valve due to it being turned by X degrees, right? How much pressure are we losing? Or what's our hydraulic loss across this valve, right? And so I'll close out of this cross section here. And so right now I'm in Creo Parametric, but again, the same thing happens for, NX, Solid Edge, in SolidWorks as well. Yeah, it's going to be the same or very similar UI to how FloEFD is going to work. And the way it's going to look is this over here. So inside of Creo, this Flow Analysis tab is a FloEFD enabled tab, right? Whenever I pick on that, I have all of the flow, all of the parameters I need to put in or to analyze a CFD model, right? PTC that makes Creo Parametric, they do not have anything at all that does any flow analysis. And so everything in here, flow analysis, is entirely FloEFD, right? And also this blue FE button over here is also FloEFD as well. So that is your FloEFD project tree that basically walks you through, all the different components and items you have in your project, right? So in this case, I'll go ahead and start and set up this this other project over here, right? And what I'll do here is, let's see. So to start off, we'll start with our wizard, right? And so again, FloEFD is very easy to use and wizard based, right? So all I just have to do is, follow the bouncing ball, click next, 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 right? For a lot of the setup. So I can basically give my project a name. I'll say, let's see here. I can choose whatever unit system I prefer, and this will typically default all measurements in FloEFD to that specific unit system, but you're not limited to that. If you enter a different unit, it will it'll use that. So in this case, I'll just keep it as the SI unit and continue. Let's see, this is going to be an internal analysis, so I'll leave that internal radio button selected. And currently, we don't need any of these physics in this model. This is just going to be flow only, so we'll leave those as is right now and just hit next. And the fluid in this case is going to be water. So FloEFD comes pre-built with very good material library that you can use. In this case, I'll just add water, it's liquid, to that, and just hit next. And finally, I believe, yeah, that's everything we're going to do as a setup inside of this wizard initially, right? And now you'll notice FloEFD automatically recognizes the flow domain and uses this black wireframe box to show that, right? Again, I can verify that by picking on the show fluid right here. And let me get rid of this guy. Yeah, there we go. And FloEFD automatically shows you, okay, that's what I understand your flow domain to be, right? I don't have to do a bazillion fancy things. I don't have to, close surfaces or do whatever. The software is smart enough to, understand and recognize your native geometry itself. You'll notice I didn't even have to export anything at all, a step file or native file to a different software package. I'm working straight within my CAD software. All right, and so now I'll start introducing some boundary conditions. So we'll say in this case, let's see, for Creo, I'll switch this to geometry. I'll pick on a surface, and now I'll say I want this to have an inlet flow rate of about 1 meter per second. So basically 1 meter per second of water is flowing through that face into the valve. And on the other side, that's going to be a environment pressure, so it's basically going to be open to the atmosphere. So I'll switch this and say that's going to be environment pressure, and we'll say OK. All right. Or actually, I'll modify this a little bit and switch that to static pressure, but still keep the same values, right? And then next is FloEFD works with goals, right? So basically, a goal is a quantitative value or data that you're interested in your model that that you need to get out of your CFD analysis. And you can tell FloEFD those goals ahead of time, and you can also have FloEFD converge on those goals as well. So that way it ensures that it's accurate on exactly what you're converging on, right? And so in this case, or exactly, it's converging on what you're interested in, I should say. So in this case, I will specify that I want a goal on a surface, and you'll notice it brings out a list of different goals that are applicable. And for me, in this case, it's just as easy as checking a box to say I want the average total pressure, right, across this inlet face over here. And I'll also hold Control and pick the outlet one as well. So basically, I want the average total pressure across both faces, and I'll say let's create a goal for each face, and we'll say OK to that. Yep. And now I have an average total pressure goal for the inlet and also for the outlet as well, right? We'll go over to our mesh settings, and for this case, I'll just tweak this value in here so that way it recognizes the smallest gap in our model, right? And we'll keep this here at the default, mesh over here of 3, and we'll go with that, right? And so now we'll say let's go ahead and run this. And FloEFD will pull out this monitor right over here. And you'll notice something right here, right? It shows me a warning and says a vortex crosses the pressure opening, right? And so that's a case where you have some recirculation either at your inlet or your outlet, and that could lead to very, very wrong results in CFD, right? But the solver is smart enough to recognize that and put that in there as a warning for you, right? And so now I can just stop this because it's not going to be any use to get those results. And ordinarily what that means is we're going to have to increase the entry length for the inside of the leading into the valve and also after the valve as well, right? Now because I'm CAD embedded, right, I already have some of those configurations inside of Creo, right? I have those in here for my 40 degrees long valve. I already have that set up. Now if I want to pull that into FloEFD, all I do is I take my existing setup. I don't have to change anything. I don't have to reset it up all over again. I just say, let's clone this. And this time, I want you to use the 40 degrees long valve. We'll say OK. And FloEFD recognizes the flow domain has changed, so it's going to reset that as well, right? And you'll notice now I have a longer flow domain, different model, inside of the same software with all of my same setup, the same inlet velocity, static pressure, goals, and everything, right? The only thing I have to do is now hit run to continue this analysis, right? So again, it's not a case where you have to, export it all over again, export a step file, manage any, geometry issues you have, and dance with all of that. The software is intelligent enough to just clone with your CAD tool and then continue along, right? So what I'll do here is I'll switch over to a different, or I guess I'll give this here a couple seconds until it finishes. Yep, it's already done. And so now what I'll do here is we'll say let's display a couple different things, right? So I'll pick on, see, show a cut plot. Yep, like that. And I want to show velocity in the X direction. Yep, and I'll also show some flow vectors as well. and we'll hit apply. Actually, let me switch this as well. So 0.02, 0.001. Okay, so we'll apply that. Now, currently, we can't see that, cut plane because it's inside of the model, right? Well, FloEFD has a handy dandy tool right here to basically hide the model and show you, exactly where your cut planes are. So in this example here, the vortex that I initially had, where it warned me about, was somewhere right around here, right? And you can clearly see that, in this case with the fringe plot, right? Now, again, in order to better analyze our flow and see areas of vorticity much easier, one of the tricks we usually do is just come edit this here, set this to 3 legend levels. And let's see. Oh, edit this guy. Hold on, I think I'm missing that button. So set this to 3 legend levels. Oh, sorry. This is what I kept glossing over. So we'll set this over here to from -1 to 1 for our velocity value in the x direction, and then we'll hit go. So essentially, what this is showing is our flow should be going from left to right in the x direction, right? And anywhere that's blue has negative x flows. So essentially, anywhere that I see is blue, there's some recirculation happening, right? So red flow is going to the right, blue flow is going, to the left. And so that, again, gives you an idea of areas of vorticity, in this case, in your model, right? So one of the other things I'll do here is we'll say, let's show the total pressure, because, that's what we're interested in this case for this, this model. So I'll say, yep, pick on total pressure, move this over, apply, yep, and now this shows, the total pressure as a fringe plot from, the inlet all the way through to the, to the outlet over here, right? Now, again, I also ask it to get those total pressure values as goals. I can right-click on the goal over here. I can let's see, okay, I can select which goals I want to show, in this case both of them. I can show them inside of the window over here, inside of Creo, right? The average, the minimum, and the maximum values. If I prefer, I can export this to Excel, and in one click, FloEFD passes that information onto Excel, right? The same happens as well for graphs and plots, right? So for example, this is a plot of, that goal as it's iterating through until convergence, right? So we'll close that for now, say okay. And so now, in order to calculate the pressure loss, or I guess across this particular valve, I could put it in as a goal, as an equation goal. I could have set it up for FloEFD to automatically calculate it out as it's running. And I believe I did this in one of our prior webinars on simulating airflow using FloEFD about 2 to 3 months ago. And that, again, is on our YouTube page. You can go there and check that out. But in this case, I want to show something a little different inside of FloEFD. So what we'll do is we'll come over here to this Tools, and then pick on Calculator. And it pulls out this Excel-looking spreadsheet. And what FloEFD already has is some built-in formulas and calculations that we already have, right? So for example, in this case, if I want to calculate the total pressure loss, right, I can come over here and tell FloEFD, hey, pull in the formula for total pressure loss, right? So again, part of what this lets you know is you don't have to spend, a bunch of time Googling, oh, what's the formula for the critical velocity, or, what's the formula for this, and then having to convert back and forth in Google or whatever, or looking back at your reference notes or textbooks. All of this is, stored right in here for you inside of FloEFD, right? So I'll have it insert an existing formula, right? And now running the calculation is as simple as just typing in values, right? I know I put in my inlet velocity as 1, right? I know the density of the water that I gave it is a certain value, so I'll just type those in. Yep. And then I know from the analysis, it told me that there's a certain pressure at the inlet and the outlet, so I'll type those in. So that's, oh, no. Yep. And when I'm done, FloEFD tells me, hey, that's your result. That's the total, pressure loss across that valve for this particular flow case, right? Now, again, I can, because I can, what's it called? So because our goal in this case is to see what the delta is just because of the ball itself, what we'd have to do is rerun this analysis where the ball is set to 0 degrees and everything is fully inline, right? And then we can see the delta between this case here at 40 degrees and the and the 0 degree case, right? Now, thankfully, that has already been run, so we're not going to go through that. A lot of that setup is the same. But again, just to sort of, to sort of show here, if I was going to do that, all I would do is just say I want to clone this project. Say I want to use a specific configuration and pick on this 0 degrees long valve. I check that box and it'll automatically, change the model and set that up. But in this case, what I'll do is I'll just go to the calculator and open an existing calculation where we already have the results saved. So let's see, hydraulic loss. Well, where we hope the results would have been saved, I'll put it that way. Let me see if I can hunt them down really quickly here. Nope, it's not here, so that's fine. I'll just go ahead and put those in. So do this again. Say I want a formula. Okay, and we'll do the same over here as well. Same formula. Total pressure loss. Okay, and let's see. These guys are going to be yep. And let's see, for P1 and P2 for the 0 degree case, those are set to, let's see, 1, 2, 0, 2, 8, and yeah, they're about. And so, yep, now the pressure loss just across that ball, just as a result of it being turned 40 degrees, is as simple as, 26.7 minus, 0.39. So that's right around, 26.3 or so for the pressure loss across there, right? So again, this goes to show how easy it is for you to calculate things inside of FloEFD and run a quick flow analysis inside of it here, right? Now I notice I'm a teeny bit short in time, so I had an additional example here I was going to show, but I won't show the setup. All I'll have to show is the final results of that one. So in this case here, let's see, hide my flow domain. Oh, hide that. Okay, so in this case here, what we have is essentially a heat exchanger. So do this from the X direction. Yeah, so what we have is a heat exchanger where air comes in from this section here, this yellow pipe or channel in here. So hot air comes in, flows through into this red section, and then flows out of the other side over here. And likewise, cold water or cool water comes in from this pipe over here on the right, flows through into this, cylindrical cavity around the hot air, and then flows out through here as well, right? And then so the goal is to find out, how accurate, or I guess how what the efficiency of your heat exchanger is, right? Now again, this is a simple case, for where you just have simple geometry for a heat exchanger, but again, you can extrapolate the results to to a broader context, right? So in this case, let's see, what we'll do here is just give me a second here. Okay, so to show the results over here, I will create a cut plot, and we're basically just slicing the model through the middle, and we'll see. Let's say I want to show the temperature, everything, solids included, and we'll say OK. And then let's see, I'll use my display button over here to hide the existing model so you can see what's going on. Again, yeah, and you have your legend over here to see that. Now, this legend isn't as descriptive of what's going on, so I'll switch this here, and so let's set this to about 300 Kelvin. And now you can clearly see what's going on, right? So, cool air, cool water comes in from this end over here, and as it flows through the heat exchanger, it gathers some more heat. It sucks heat out of the air flow in the middle, and the water coming out of this end over here is much warmer or much hotter, right, than coming in. And again, you can now use this to compare, your temperatures at the inlets and the outlets of both fluid streams, and then start to, calculate quantitatively what your heat exchanger efficiency is, right? So again, I just did this to show, what some of the things are that you could do in terms of capabilities with FloEFD simulating liquid flows, right? So at this point, I'll open it up for questions. So if you have any questions, go ahead and type them in the questions pane of your GoToWebinar control panel, and we'll go ahead and answer those live right now. All right, so we already have a few questions, and we'll just go ahead and step through those. So one of the questions is regarding pricing. Can you provide a ballpark on the price range per user? That I would have to defer to sales on, and so I'll forward that question to our sales team, and then someone from there will follow up with that user. Someone here asked, is a smart cell and a partial cell the same? And I believe that's referring to the PowerPoint where I was describing what goes on in the boundary layer. And the answer for that is yes. Smart cell and a partial cell is the same. Essentially, within the smart cell, part of what because it exists, because it's not entirely fluid and it's not entirely solid, it always exists at the boundary where you're crossing between a solid and a fluid. And so that is a smart cell, and it basically has part solid, part fluid. Yeah, so it's terminology-wise, it's the same thing. So the next question, is a different configuration just defined as a family table or a simplified rep inside of Creo? And so I'll answer that question a couple different ways. So how you can get to a different configuration, there are a couple different ways you could do that. One is, as the person asked, in this example here, we define this just as a family table instance inside of Creo. No, this is the long valve. So let me activate this guy. Yeah, so these are just family table instances, right? And it'll understand and use those family table instances as different values. The other thing you could also do inside of FloEFD, and I believe I went into some depth with it in a different webinar, but the other thing you can also do with this is, no, close this guy, turn on. Okay, yep, unhide the model. So let me go turn on my parameters in this case inside of Creo. So, or I guess turn on my features so I can see what features are used to create this this model here. Okay. So for example, I can see here this Revolve feature created this middle section of the part. So if I right click and I edit that, I can see the dimensions that created that, this middle section right here. I can see, this dimension here, that's 0.06, that's, radius of a certain value. And I believe I'll probably go into more depth in a different webinar about this, but in FloEFD, one of the things you can do is you can create a parametric study where now, for example, I could let's see, add a dimension from Creo, and now I could pick on an existing Creo dimension, for example, this R12 dimension, right? And I could say, hey, let's add that as a parameter, and FloEFD, I want you to change that, I don't know, for example, say, try 0.12, try 0.15, and also try that 0.18, right? And if I hit OK and I run this, it'll run this model for all those three different values, right? So again, I'll probably elaborate on this more in a different webinar where we go through a lot of detail in the parametric studies. But for now, yes, you can also manipulate your model a couple of different ways. All right. So another question is, let's see here. Do you have any examples of pumps and rotating parts? Yes, we do have those. We do have those. I don't have those currently on this computer. I don't believe they're even solved, and so I would have to set that up, and I'll reach out to that particular user and show on a one-on-one session, what that would be for pumps. And then another person here is asking how accurate are the results of this software? And so just to sort of get an idea of how what the accuracy is. Well, the best thing I could sort of say to that is to use a PowerPoint. So hold on a second while I grab a PowerPoint here that sort of walks through the accuracy in this case. So. And let me see here. Let's see. No, I'm having difficulty finding that that particular PowerPoint right now. But yeah, whenever I do that, whenever I find that, I can probably make it available. Basically, there's some what's it called, benchmark studies that have validated FloEFD versus other CAD versus other CFD codes, and they've had FloEFD to where it's within within a very accurate percentage of other CFD codes, and also of real world testing with a fraction of the solve time. So again, I guess I'll give a couple examples. Uh, One of the models we have is FloEFD solving the temperature on an LED light bulb. And this is actually a case study from a customer. FloEFD predicted the temperature of the LED to within 2 degrees of the actual value. And so again, and so they basically built this LED out in the real world, tested it out, and FloEFD's prediction was within 2 degrees of the actual value, right? You also have an example where we just did this for a customer. They had a flow simulation where they were trying to calculate the pressure loss, and they already had some tests that were done in, I believe it was Fluent, and FloEFD was within 0.5% of the Fluent calculation, right? So yeah, I couldn't find a PowerPoint that sort of speaks to that broadly, but I can at least give those examples to get you to let you know how accurate the software is. Yeah. All right. See any more questions? Okay. Someone else also asked here. How did you know to make the output port longer to solve the vorticity issue? That, I guess in general, that is, I don't want to say common knowledge in CFD, but in general with CFD, the knowledge that vorticity could influence or your inlet or your outlet, and in general extending your inlet or outlet regions 5 or 10 times the characteristic length of your model is preferable. That is in general typically applicable in a lot of CFD, and so that's just especially whenever you have a case like this here where there is no inlet or outlet region whatsoever. That is in general one of the easiest checks to do, is just to add some length after your flow region, and then rerun the analysis again. And another question here, does FloEFD have the capability to run transient analyses? And the answer for that is yes. Yes, we do have the capability to run transient as well as steady state analyses as well. In fact, one of the transient analyses we did for a customer recently was a case where they wanted to, they're making a thermos flask, in this case where, so there's minimal heat loss through conduction and minimal through convection, but it does exist. Primarily it's through radiation. And also it's a time varying thing, right? So heat loss varies as you go in time. And FloEFD was able to predict, how long can your thermos flask sit in a, for example, 80 degrees Fahrenheit room before it, cools down to a certain temperature, right? So the cool down time. All right. So we're pretty much at the end of the webinar here. I know there were a couple of questions that we didn't get to live on here. I'll go ahead and actually, hold on. One question just came in about CFD analysis export capabilities. Yeah, I'll just go ahead and answer that one real quick because that's easy and simple. So I can hit over here under results and or no, not results. Yeah, tools, and there's my export results option. So say, for example, in this case, I just showed you guys, and then we'll come over here. We'll load this. Actually, no, we'll come to this one here. No, why can't I find it? Okay, yeah, this is the one. Yeah, so I just showed you, for example, how we have a lot of, how we have this the total pressure plot, for example, inside of this model, like that. Now, if I want to export this to an FEA software, so that way I can then run a stress analysis on, the steel that's going to build this ball valve, so I can see how much stress is going to develop in the steel, based on just the pressure pushing on this. Yeah, I can do that, and it's just as simple as picking here tools, export results, and then I can tell it, okay, I want to export pressure results. And I can choose what software I want to use. I can export this to, Creo Simulate. That's the native FEA software for Creo. I can export this to some neutral formats as well as to Abacus, Nastran. I could also, if I had SolidWorks simulation, I could export this to SolidWorks simulation as well. And also, I believe Solid Edge simulation as well. But in this case, I don't have any of those installed, so I don't get the option here. But yeah, I can export this to whatever FEA software I want, tell it what I want the loads to be, and yeah, I can just hit export and it'll create that file immediately. Yep. But okay, so we're exactly at 12:30, right on the hour, and so we'll go ahead and stop the webinar right now. Thank you so much for attending. If you have any other questions or comments, don't hesitate to either email us at marketing@boundariesys.com, or you can email me personally. My email is, you can just copy it from the GoToWebinar control panel there. Thanks again, and we'll see you next week on another edition of Boundaries Webinar Wednesdays. Thanks. Yep. Bye.